Welcome to What Is, where we take the infinitely complex, the infuriatingly abstract, and the I definitely should have paid more attention in 10th grade geometry topics and break them down to something we can all understand. Today we're going into the rabbit hole. Actually, it's not just a rabbit hole. It's a rabbit hole that when you look closer is made up of smaller rabbit holes, which in turn are made up of even smaller rabbit holes, theoretically forever. Today we're talking about fractals. Now, before you go reaching for the back button because you heard the word math, stay with me. This isn't the kind of math that involves solving for x while a train leaves Chicago at 60 miles per hour. It's the math of clouds. It's the math of lightning. It's the math of your own heartbeat and the way your lungs breathe. It's the secret code of the universe, and once you see it, you will never look at the head of broccoli the same way again. Seriously, Romanesco broccoli is basically a geometric crisis waiting to happen. To understand a fractal, first we have to understand what it isn't. Since the time of the ancient Greeks, we've been obsessed with Euclidean geometry. You know the hits: the circle, the square, the triangle, the sphere. This is the geometry of perfection. It's smooth, it's predictable. If you zoom in on a perfect circle, eventually the curve starts to look like a straight line. It's clean. The problem is, nature doesn't give a hoot about Euclidean geometry. Have you ever seen a perfectly spherical mountain? Or a cloud that's a perfect cube? Of course not. Nature is jagged. It's tangled. It's messy. For centuries, mathematicians looked at the roughness of the world and just sort of ignored it. They called it pathological. They thought it was too ugly and chaotic to be measured. But then came the 20th century, and a man called Benoit Mandelbrot. He decided that roughness wasn't the mistake, it was the point. So, what is a fractal? In the simplest possible terms, a fractal is a shape that is self-similar. Imagine that you're looking at a tree. You see the main trunk splitting into big branches. If you take one of those big branches and cut it off, don't actually do this, the tree needs it. But if you did, and you held it up, it looks like a smaller version of the whole tree. Then look at the smaller twigs on that branch. They look like even smaller versions of the branch. This is the core concept of a fractal. The closer you look, the more of the same detail you see. It's like a Russian nesting doll, but instead of dolls getting simpler as they get smaller, they stay exactly the same level of complicated. Think about the coastline paradox. This is the classic example Mandelbrot used to blow everyone's minds. If I asked you, how long is the coastline of Great Britain? You'd go get a map and a ruler, and you'd tell me it's about 2,800 miles. But if you went down to the beach with a 1-foot ruler and measured every single nook and cranny, every little inlet and jagged rock, the length would be much longer. Now imagine you use a microscope to measure every single pebble, every single grain of sand, and every single molecule. As your ruler gets smaller, the coastline gets longer. In theory, if you have an infinitely small ruler, the coastline is infinitely long. That's a fractal. It's the finite area bound by an infinite perimeter. It's a shape that exists in the in-between dimensions. It's not quite a one-dimensional line, and it's not quite a two-dimensional area. It's a fractional dimension, hence fractal. Mind blown yet? Good. We're only 4 minutes into the trip. Grab a snack, maybe some romesco broccoli, get a good look at it, and let's talk about how this concept actually developed, because the history is just as jagged as the shapes. Before we had the word fractal, we had mathematical monsters. In the late 1800s and early 1900s, mathematicians like Georg Cantor and Helga von Koch were starting to doodle things that made their colleagues very uncomfortable. Koch created what we now call the Koch Snowflake. You start with an equilateral triangle. On the middle of each side, you add a smaller triangle. Then you do it again and again and again. The result is a shape that looks like a snowflake, but if you keep going forever, it has an infinite perimeter, but fits inside a small circle on your paper. This broke people's brains. They thought these shapes were monsters because they didn't follow the rules of normal math. They were too weird to be useful. Then came the Great War, and two French mathematicians named Gaston Julia and Pierre Fatou. They were working on something called complex dynamics. Julia, by the way, was a certified badass. He was injured in World War I where he lost his nose. He spent the rest of his life wearing a leather strap across his face while doing some of the most complex math in history. Julia and Fatou discovered that if you take a simple equation and feed the answers back into the equation over and over and over, you get these incredibly complex sets of numbers. This is called iteration. Imagine a feedback loop. You know when a performer puts the microphone too close to a speaker and you get that piercing screech? That's iteration. The sound goes into the mic, out the speaker, and back into the mic. It gets amplified every time until it becomes a monster. Julia and Fatou were doing this with pen and paper. They were trying to visualize what these feedback loops look like, but they couldn't. Not really. Humans aren't built to do 10 million calculations in a row, so the Julia sets remained these beautiful, ghostly ideas trapped in the mind's eye of a man with a leather mask. Enter Benoit Mandelbrot. We mentioned him earlier. It's the 1970s. Mandelbrot is working for IBM. Now, IBM at the time was the king of the big box computers. These were the rooms filled with spinning reels and humming vacuum tubes. Machines with less computing power than your modern toaster, but they were the best we had. Mandelbrot was a bit of a rebel. He didn't like being pigeonholed into one field. He looked at the noise in telephone lines, static that IBM couldn't figure out. He realized the static followed a fractal pattern. He looked at the way cotton prices fluctuated over 60 years. Fractal pattern. In 1980, he decided to use IBM's computers to do what Gaston Julia couldn't, actually see the math. He took a very simple equation, z equals z squared plus c. Don't worry about what the letters stand for. Just think of it as this little machine. You put a number in, it squares it, adds another number, and gives you a result. You then take that result and put it back into the machine. If the number stays small, it's in. If the number grows to infinity, it's out. Mandelbrot programs the computer to plot these numbers on a graph. If a number stayed in, he colored it black. If it flew off to infinity, he colored it based on how fast it escaped. When the printer finally spat out the image, he thought the machine had glitched. It was a weird, bulbous shape that looked like a cardanoid, a heart, with circles budding off it. And those circles had smaller circles. And the whole thing was covered in these weird prickly thorns. He cleaned the dirt off the image only to realize the dirt was more of the shape. He had discovered the Mandelbrot Set. It's often called the fingerprint of God. The Mandelbrot Set is the most famous fractal in existence. It's an infinite territory. You can zoom into it forever. You can spend your entire life zooming into one corner of the Mandelbrot Set, and you will never reach the bottom. You will find many Mandelbrots that look exactly like the big one, tucked away in valleys of infinite complexity. This was the turning point. Suddenly the monsters weren't monsters anymore. They were a map. Mandelbrot wrote a book called The Fractal Geometry of Nature in 1982. It changed everything. He argued that we've been looking at the world all wrong. We've been trying to describe mountains as cones and trees as cylinders. But a mountain isn't a cone. A mountain is a fractal. This leads us to the meaning part of our journey. Why does this matter? Is it just pretty pictures for stoner dorm room posters? No. Fractals are the reason you're alive. Let's talk about your lungs. If your lungs were simple balloons, they wouldn't have enough surface area to absorb the oxygen you need to survive. But your lungs are fractals. The trachea splits into two bronchi, which split into smaller bronchioles, which split into smaller tubes, and so on. By using a fractal branching pattern, nature packs in a massive amount of surface area, about the size of a tennis court, into the tiny space of your chest. Your circulatory system, fractal. Your neurons, fractal. The way your heartbeat fluctuates. If your heart beat like a perfect rhythmic metronome, you'd be dead. A healthy heart has a fractal variability to its rhythm. Chaos, it turns out, is a sign of life. Fractals are the efficiency code of the universe. If you're a tree and want to catch as much sunlight as possible without spending too much energy growing, you use a fractal algorithm. You don't need a complex DNA blueprint for every single leaf. You just need one simple rule: grow, split, repeat. This discovery revolutionized more than just biology. It changed the way we build the world. Think about your cell phone. If you're old enough, do you remember when cell phones had those little pull-out antennas? They were annoying, they broke, and they were basically just Euclidean sticks. Then, a radio astronomer named Nathan Cohen, who had studied Mandelbrot's work, had an idea. He was being told by his landlord that he couldn't have a giant radio antenna on his roof. So he took some wire and bent it into a manga sponge, or a Koch Snowflake shape, a fractal antenna. Because of the infinite perimeter in a finite space trick we talked about earlier, his tiny folded up wire could pick up a massive range of frequencies that worked better than a straight stick. Today, almost every smartphone on the planet uses a fractal antenna hidden inside its case. You are literally carrying a piece of infinite geometry in your pocket. And then there's the movies. In the early 1980s, computer graphics were, well, they were bad. Everything looked like Tron: smooth, plastic, and fake. Creating a realistic mountain or a cloud was impossible. You couldn't hand draw every crag on a mountain range. It would take 1,000 years. But then a guy called Lauren Carpenter, at a little known startup you might have heard of called Pixar. Actually, it was Lucasfilm's computer division at the time. He saw Mandelbrot's work. He used a fractal algorithm to create a mountain range for a 1980 demo called Paul Le Bear. When he showed it at a computer graphics convention, the audience lost their minds. They didn't think a computer could create something that looked so real. A couple of years later, he used the same trick to create the Genesis planet sequence in Star Trek II: The Wrath of Khan. That was the first time fractals were used in a major motion picture. Today, every time you see a digital explosion, a CGI ocean, or a realistic forest in a Marvel movie, you're looking at fractals. But the meaning of fractals goes even deeper than technology. It touches on philosophy. For the longest time, we thought of the universe as being divided into two categories: order and chaos. Order was the planets orbiting the sun, predictable, mathematical, Euclidean. Chaos was the weather, the stock market, the way cream swirls into coffee: random, messy, incomprehensible. Fractals bridge the gap. They show us there's an orderly chaos. A fractal looks chaotic at first glance, but it's actually born from a very simple, very orderly rule. It tells us that the complexity of the world isn't an accident. It's the result of simplicity being practiced over and over and over again. It's a beautiful thought, isn't it? The crashing waves, the formation of galaxies, and the vessel of a tiny leaf are all speaking the same mathematical language. It also changes how we think about size. In a fractal world, scale is relative. If you look at a photo of a fractal, you can't tell if you're looking at a microscopic crystal or a mountain range on Mars. There's no preferential scale. The universe is beautiful at every level of magnification. So let's recap before your brain starts to undergo z equals z squared plus c levels of iteration. What is a fractal? It's a shape that's self-similar across different scales. How did it develop? It started as mathematical monsters in the minds of geniuses, and survived the World War, or two, and was finally brought to life by the birth of the computer and the wandering mind of Benoit Mandelbrot. And what does it mean? It means that nature isn't broken or messy. It means that the jagged edges of our world follow a hidden logic. It's the math of growth, of efficiency, and of beauty. It reminds us that even when things seem chaotic, there might be a deeper pattern underneath. And even when things seem simple, there might be an infinite depth waiting for you if you're willing to look just a little bit closer. Next time you're outside, take a look at a fern. Look at the way each little frond is a tiny copy of the whole branch. Or look at the clouds, or your own hand. You're a walking, breathing, thinking fractal. You're a finite being containing an infinite amount of complexity. And if that doesn't make you feel a little bit more connected to the universe, I don't know what will. Maybe try eating some of that romesco broccoli we talked about. It's actually quite delicious with a bit of garlic and olive oil. Just try not to get lost in the geometry before you finish your dinner. Before we go, I want to leave you with one final thought. Mandelbrot once said, "Bottomless wonders spring from simple rules repeated without end." Think about your own life. What are the simple rules you repeat every day? Your habits, your thoughts, your small choices. They might seem insignificant in the moment, but over time, they iterate, they build, they create the complex beauty and sometimes chaotic fractal that is your life. Make sure you're choosing the right equation. Thanks for joining us on this Zoom into the Infinite. If you enjoyed this journey through the What Is Vault, do us a huge favor. Hit that like button. It helps our channel grow in a very, well, let's call it non-Euclidean way. Subscribe to more deep dives into the concepts that make our world what it is. If there's a topic you always wanted to understand, whether it's quantum entanglement, the history of sourdough bread, or why we haven't found aliens yet, drop a comment below. We read them all, and your suggestions might be our next 20-minute rabbit hole. Stay curious, keep looking closer, and remember, it's fractals all the way down. See you next time.